So today we talked a little bit about Hess's law. I gave you a problem to do. I'm just going to give you a few notes on it so that you can make sure that you have a good understanding. So here we go. So Hess's law basically states, and it was developed by Germain Henry Hess, which is a German guy who came along and basically said that it doesn't matter how we get there. How we get there doesn't matter. All that matters is that we get there. So the pathway doesn't matter as long as we get to the right answer is basically what he's saying. So if we go from one particular set of reactants to another particular set of products, the change in enthalpy is the same whether it takes place in one step or a series of steps. So you can see that the green path is a single step that goes from reactants to products. But path B takes multi-steps. There are actually like 3 different steps there. We go from reactants up to an intermediate, down to another intermediate, up to a third, and then down to the products. It doesn't matter because eventually what ends up happening is the amount of energy is the same regardless, because we only have a certain amount of energy between those two things. And whether or not the pathway takes us up and down, by the time we subtract everything down, we're going to get the same answer. So we can use different equations to calculate the delta H, as well as just calculating the delta H normally by taking the reactants minus the products. So there are 2 ways to approach this problem. So the first way we talked about today in class is Hess's law. So we calculate delta H for the combustion of methane. So there's the combustion of methane. Okay, here are the reactions that we can use to try to work with the combustion of methane. So the first thing we have to do is figure out how we can take these things. Well, I see that I'm going to need CH4. I'm going to need some CH4. So I'm trying to find some other color that we have. So CH4 is found right here, but it's on the wrong side. So I'm going to have to take that and probably flip it. So step 1, CH4 must appear on the reactant side. So we reverse it reaction 1 and change the sign on delta H. We don't have to multiply it because we only need 1 methane. So we're all good there. So there's the first equation. So see how I flipped this first equation to get CH4 on the other side, and I changed the sign on delta H because I flipped it. So now I have to get some O2 in. And I see my O2. So step number 2 is keep the reaction number 2 unchanged, because CO2 belongs on the product side. So we need CO2 on the product side here, and we have CO2 on the product side here. I only need 1 of that, so I just put that reaction in. I keep it the way it is. I don't do anything to it. Okay, then I'm looking for H2O, but I have to have 2 H2Os. So to get 2 H2Os in there, I have to multiply reaction number 3. It's actually number 3. That should be 3 by 2. So I'm talking about this one right here. This one has to be multiplied by 2 to get the right thing to come out. So I multiply that by 2 and I get this. And notice I also multiply the delta H by 2. All right? So now I go through and make sure that everything cancels out that's supposed to cancel out, because I just need what I need. So I can see C is going away, H2 is going away, leaving me with CH4 plus 2O2 plus CO2 plus 2H2O. So we see that we have the right equation. So sum up the reaction and the delta H. So here we go. All of that canceled out that I just said, leaving us with that, and then we add the delta H together and we get negative 890.36 kilojoules. This is how you use Hess's law. Don't panic. It's not hard. It's just a puzzle. You're given a set of equations and reactions with delta H's, and you're looking for the pieces of the puzzle that give you the overall reaction and cancel everything else out that you don't need. Now, we would normally calculate delta H for combustion of methane in a little bit of a different way. We would be given that the delta H of the reaction, the whole reaction, is the sum of the delta H of the products minus the delta H of the reactants. It's always that. Anytime we do any calculations with equations, it's always the sum of the products minus the sum of the reactants, whether it's delta H, delta S, delta G, it's always the same. So please make sure that you realize it's products minus reactants, final minus initial. Always for delta, final minus initial, okay? So we're given information about the delta H formation of all of these things. So I see the delta H formation of CH4 is 74.8, okay? O2 is 0 because it's elemental. Any elemental is 0 formation because it just occurs like that. CO2, we see the formation of that one, and then H2O, we see the formation of that one. So what are we going to do? Well, first of all, we have to think about stoichiometric mean. So we can see that this one right here is multiplied by 2, but so that guy's got to be multiplied by 2 as well. So then I'm going to add these two pieces together for the sum of the products. I'm going to add these two pieces together for the sum of the reactions. I'm going to subtract them from one another. So I see I have, this is the sum of my products right here, okay? And then minus the sum of my reactants right here. And I get minus 890.36 kilojoules. So here we have two different methods to finding delta H, and it doesn't matter which method I use because I get the same answer no matter what. And you're going to say, well, those numbers look the same. Well, because they're reactions describing some similar things, but these are numbers that you can look up on a table. So any type of delta H of formation are numbers that are given to you in a table, and I'll probably be giving you a table of those tomorrow. All right? Thank you very much, young people. So sorry if it confused you.